So we were discussing normal distribution. Today we are going to go for, in general, what is known by interval estimation. Okay. So what do I mean by interval estimation? See, statisticians generally don't like to provide single value as estimate. Okay. So we saw some example last time. So if I am talking about, say, height of individuals, so I could record height of, say, 100 individuals, x1, x2, x100 be the heights of 100 individuals in my sample. Then for the population mean we give x bar as estimate. Okay, that is fine, but we don't like to stop at x bar, because we know that if I have x bar here on this graph, then we know that for this particular sample my x bar is here, but for the actual population, the population mean could be here, here, here. Yeah. So my x bar is here, but that doesn't mean that my population mean would be exactly here. Population mean could be at any of these places, right? In fact, we saw the concept of sampling distribution. Do you remember? So what we said was, if suppose someone else takes up a sample, then that person is going to get a different value of x bar. A third person will get some other third value of x bar, and so on. So that's why statisticians generally don't like to provide just a single number as estimate. Okay. So we try to do what is known as interval estimation. So while providing this x bar, along with this x bar, we also provide some upper and lower bound, some sort of interval, and it is known as 1 minus alpha % confidence interval. Okay, so the word that is used is confidence interval. What do I mean by confidence interval? So this is confidence interval for population parameter. So here population mean. Okay. So what is meant by that? So this actually means that my interval has, generally we take alpha to be 0.05. So my interval has 95% chances of capturing the actual population mean. Okay, let me repeat. If I provide this interval, let me call it, say, A to B, and this is my sample mean. So my sample mean, okay, so sample mean tells me that population mean is going to be somewhere near this, but when I say somewhere near, how near or how far, that is judged by this interval. So on the basis of current sample, I would say that my interval AB has 95% chances of capturing the population mean. Okay, is it okay? Why 95%? Why not 100%? See, if I want to give 100% interval, then it would be too wide, because I will have to consider all extreme possibilities also. Okay. For example, if I am talking about, say, rainfall in a particular day, and if I want to give 100% confidence interval, then I have to consider even the extreme cases like floods and droughts, and in that case my interval will be too wide, it will actually be meaningless. So we don't go for 100% interval, we generally provide either 90% or 95% or 99% interval, depending on requirement. So if we want to be very confident that things don't go outside our interval, then we go for 99% interval, which is of course wider than 95% interval. So how do we construct that interval? That is of interest to us right now. Okay. So we construct this interval by computing variance of the sample mean. Variance of the sample mean. So we talked about sampling distribution. So what did we say in sampling distribution? We said that if suppose one person does this exercise and gets some value x1 bar, another person does the same exercise, means that person contacts some other 100 people, records their height and then gets x2 bar as the average height of those 100 people. Some other person gets x3 bar and so on. I repeat this exercise say with 50 people, then I have so many values, and these values are most of the times near to each other. So their spread I can denote by some histogram, which would give me what is known as sampling distribution of my sample mean. Okay. So this spread or dispersion needs to be captured. So for that we need to see what is variance of x bar. Okay. Variance of individual observations you know how to compute, right? You have seen the formula for variance. So you know variance of xi in general will be 1 upon n sum over I going from 1 to n xi minus x bar whole square, correct? This is how you estimate sigma square. Okay, this formula everyone knows, right? Hello, do you know this formula?
Yeah, we know it.
Yeah. So now using this formula I have to talk about variance of x bar. Now what is x bar? X bar we know is 1 upon n summation I going from 1 to n xi, and we generally assume that these xi's are IID. IID means independent and identically distributed. Okay. So they are not correlated. So height of one person need not depend on height of other person. So this becomes 1 by n square, because this is when it comes outside the variance it becomes square, summation variance of xi, correlations are 0 because they are independent. So this becomes 1 upon n square, and we know variance of each xi is sigma square. So sigma square, sigma square, sigma square getting added n times becomes n sigma square. So this becomes sigma square by n. Okay, variance of x bar is sigma square by n. So if I want to compute standard deviation of x bar, that will be sigma by root n, square root of that. Okay. So this we are going to use along with the cutoffs from normal distribution. Do you remember last time we saw the normal distribution tables? So there we noticed some values 1.96, 1.645. So 1.96 was somewhere here. Then we said that only 2.5% values are to the right of 1.96, correct? Similarly, if I consider minus 1.96, because of symmetry only 2.5% values are to left side of minus 1.96. So overall between minus 1.96 to plus 1.96 I have all the remaining values, means 95% values. Got it? 2.5% are here, 2.5% are here. So remaining 95% are in between. Hence we use this 1.96, and we also saw z score last time. So we saw that x minus mu by sigma follows standard normal distribution if x follows normal mu sigma square. Okay. So here in this interval estimation we are going to use these results. Okay. So what we will say, x bar minus 1.96 sigma by root n to x bar plus 1.96 sigma by root 10 is my 95% confidence interval based on normal approximation. Okay. Why? So 1.96 because of this, because between 1.96 minus 1.96 to plus 1.96 we have 95% region. So when I equate x minus mu by sigma to 1.96, I get what I want. So I can actually guarantee that chances of this interval containing the population mean mu are 95%. Is it okay? Of course, I will not know sigma, so I will estimate it by this same formula. This formula, sigma square, I will estimate by this formula. So I will write it as sigma hat. Okay. So this is known as 95% confidence interval based on normal approximation. Okay. Why normal approximation? Because here, while computing this confidence interval, we assume that these heights or any variables that we are recording come from some normal distribution. That is our assumption, that more or less the shape of the histogram, if I plot all these heights, then more or less the shape of the histogram will be bell shaped. That is our assumption. And for many of the natural variables, it is satisfied without much issue. Is it okay? So if I give you some data, if I give you some values of say height for say 30 people, you can compute x bar. That will be your estimate of population mean, that will be your point estimate of population mean. Then you can compute sigma, your n becomes the sample size, so in this case 30, and then you can get these values, and that would give us interval estimate for the population mean. So we will be 95% sure that population mean is inside this interval. Is it okay? Hello.
Yes, ma'am.
Yeah. So I said here normal approximation. So generally this formula is used if my sample size is greater than 30. Okay. So generally this formula is used if my sample size is greater than or equal to 30. If my sample size is less than 30, then people use what is known as t distribution, but we need not go into those details. Okay. So just remember that if your sample size is less than 30, then you may have to use t distribution, which is similar to normal distribution but not exactly same. So if shape of the normal distribution is this, then t distribution is something like this. So the tails are thicker, okay, but it is also symmetric, etc. So but as I said, right now you don't need to bother. Right now, even if sample size is small, you can go for normal distribution. Okay. So this is confidence interval for population mean, single population mean. Okay. But similarly, I can give confidence interval for population proportion. Okay. So sometimes we are interested in estimating population proportion, like for example proportion of people who have been vaccinated, okay, and so on. So how do we estimate proportion? So p hat we estimate as number of observations satisfying the given criteria. So either people vaccinated or people having COVID or something like that. So number of observations satisfying the requirement or the criteria divided by total number of observations. Okay, divided by total number of observations. This is population proportion. So this is point estimate. Is this intuitively appealing estimate? I mean, normally also this is how you would estimate proportion. Now for this proportion also we have to construct confidence interval. But the problem is here I had sigma, so I could get standard deviation of x bar as sigma by root n. That is not the case in proportion. So we use Bernoulli distribution theory, and variance of p hat turns out to be P into 1 minus P divided by N. Okay, this is the formula. Variance of P hat is P into 1 minus P by N. Again, P would be unknown. P would be the actual proportion which we are trying to estimate. So that would of course be unknown. So what we do is we use P hat. So we say V hat of P hat would be P hat into 1 minus P hat by N. And once we get variance, rest of the procedure is exactly the same. So what we say? We say that now I have P hat as my observed proportion, P hat minus 1.96 P hat into 1 minus P hat by N in square root, because this is variance, okay, comma P hat plus 1.96 square root of P hat 1 minus P hat by N. This gives me confidence interval for population proportion. So this is 95% confidence interval for population proportion. Okay. If I want 90% intervals, I have to replace 1.96 by 1.645. That is the only change. I have to replace 1.96 by 1.645. That will give me 90% confidence interval instead of 95%. Okay so far?
Yeah.
Okay. So let us now try to solve some examples. Okay. On the basis of whatever we have discussed so far. So suppose that scores in a certain test have mean, this is sample mean. So sample mean of scores in a certain test is 66 and standard deviation is suppose 5. Okay, standard deviation is 5 for these scores. Now these scores are on the basis of say a sample of size 50 coming from one particular division. Okay, so in a school there are multiple divisions, so we took scores from only one division and this is what we got. So now on the basis of these 50 people, we have to estimate average score of 500 students who are studying in different divisions of the same school. Okay, so what I'll do, I'll first estimate mu hat as 66 because point estimate is same as the sample mean, but that is not enough. We need to give confidence interval. So 95% confidence interval for mu I would get as 66 minus 1.96 into 5 by root n is 50, comma 66 plus 1.96 5 by root 50. Is it okay? This would give me 95% confidence interval for the population mean, that is mean score for all the students of that particular school. Is it okay?
Yes, ma'am.
Same story we have to do with proportion. So suppose we do a survey of say 100 people in Pune, randomly selected, and we observe that say 70% of them are fully vaccinated for COVID. Okay, we observe that 70% of them are fully vaccinated. This is on the basis of survey of 100 people. Now I want to estimate for entire Pune city what would be the proportion of people who have been fully vaccinated. Okay. So of course my estimate will remain the same, point estimate will remain the same, but now I can give interval. So let me give 90% confidence interval this time. So 90% CI would be 0.7 minus 1.645 square root of p into 1 minus p divided by n, okay, and 0.7 plus 1.645 square root of 0.7 into 0.3 divided by 100. Is it okay? This becomes confidence interval for proportion. Okay. So what have we studied so far? Confidence interval for single mean, single population mean, and confidence interval for single population proportion. Okay. What is the use of this confidence interval? These confidence intervals give us likely values. Okay. So for example, if I compute here, now root 50 is going to be roughly around 7. So 1.96 into 5 by 7. So let me make it 2 just to, because I don't want to use calculator right now. So 2 into 5. So 10 by 7. 10 by 7 will be 1.4 roughly. Okay. So this will be 64.6, something like 64.6, and then 1.4 on this side. So it will be 67.4, something like this. Then we will say that every value in this interval is a possible value for population mean on the basis of current data, okay, on the basis of this current sample. Of course, if someone else does another survey and comes up with different values of these two quantities, then of course this interval would also change. Okay. But generally it won't change too much. That is the whole purpose, that on the basis of single sample I should be able to give some idea about what happens to the entire population. Okay. So here, as I said, average score for the entire school would be most of the times 90, we can say with 95% confidence that average score would be somewhere between 64.6 to 67.4. Is it okay?
Yes, ma'am.
Yeah. So we are going to later study what is known as testing of hypothesis. So there also we would see what is meant by these values being acceptable, why this matters. So why this matters is, suppose the school is claiming, okay, suppose the school is claiming that our average score never drops below 60%. Okay, the school is claiming that all our students are good, so our average student is our average score is always above 60%. Then in such a case, if they get this interval, then their claim is acceptable, because this interval is completely to the right side of 60%, right? 60, if I try to draw this on a graph, then I have 60 here and my 64 to 67. So the interval is somewhere here. So interval is completely to the right of 60. So such a claim can be accepted. Okay. Whereas if the school says that our average score is always above 66%, then that claim won't be acceptable, because now our interval says that some of the values below 66 are also there in the interval. Okay. So such claims are very useful when, for example, when you are talking about say new drug. So Eno gives you relief in 6 seconds, right? You always see the ad. And now you have prepared some another antacid and your claim is it gives relief in say 4 seconds. Then you have to actually prove that your entire interval is below 4 seconds. because now here less than 4 second we are claiming. Okay. So in such claims these confidence intervals are useful. It will be more we will see testing of hypothesis in detail. At that time you will be able to see the correspondence between this interval and the testing. But right now, is it clear how to compute confidence interval for population mean and how to compute confidence interval for population proportion?
Yes, ma'am.
Okay. So next what we have to do is we have to compute similar intervals for differences between two population means or differences between two population proportions. But today I will stop here. So let me stop here for today. Thank you.